Okay, so we talk about augmentation of the data structure. So the problem is, suppose we have a problem now, we need a data structure for that problem. So the augmenting means, so instead of bringing a completely new data structure from the scratch, what we can do, we can make use of the old data structure which we know, and we can do some augmentation there. We can do some we can have some extra field of information for our problem, and then which will help us to solve our problem. So that is called augmenting of data structure. So we'll take two example for this two problem. First one is dynamic order statistics. Okay, so we have seen the order statistics problem. Order statistics problem means we have given n numbers, a array of n numbers, and we need to find out. So need to find out ith smallest element. So this is the problem of order statistics. So that means we need to find out the element, we need to find out the numbers element whose rank is I. So need to find the element with rank is equal to I. So rank of an element means we have given the array or given an element. If we, so rank is the position of that element in a sorted array. So if you sort it at the position of this element. So this is the problem of order statistics, and we have seen some algorithm to solve this problem, like select, then the randomized version of the select, and then we look at the finding the good, that randomized version will take the linear time. Now then we look at the look for the good pivot, so that it will worst case it will be guaranteed linear time. So that is that we have seen. Now, so now if this set is dynamic set, so that is called dynamic order statistics. Suppose we have a set S which is dynamic set. Dynamic set means so it is changing any time the anybody can join. So dynamic set means insertion and the deletion is allowed. So these two operations make a set is dynamic. So we are allowing anybody to leap from this set at any point of time, that is deletion, and we are allowing the join a element in this set. So this set is dynamic. Now suppose we have a dynamic set and the problem is to find the ith smallest element in that set. Okay. But now the set is dynamic. So for this problem we need to have a data structure. So we need to have data structure for this dynamic order statistics. Need to have data structure to solve this problem, so that we can do this problem in a faster way. Okay. So for this we will just do the augmentation of the data structure, like we know the we have a good data structure like red black tree which is balanced. So we will use the underlying data structure as a red black tree, and then we will do some augmentation there, like we will keep some more information in that data structure, and that will solve that may help our problem. Okay, so that is called data structure augmentation. So basically the idea is to use the red black tree, because it is a balanced data structure, balanced tree. red black tree for the set S, because S set is dynamic. So, in a red black tree we can also perform the dynamic operation, the modifying operation like insertion, deletion, and but we have to do some augmentation, but keep the subset size, keep the subtree size in the node. In the nodes. So, this is the augmentation of the data structure. So, we will just use the our red black tree data structure. So, we will make the red black tree, but we will keep this extra bit of information, extra information. So, that will help us for our solving our problem. Okay, so, that means each node is having this field. This is the key and this is the size of the tree, size of the subtree rooted at that node, and this is called augmentation. This is called augmentation. So in our red black tree we have key. Based on this key we perform this, and with the key each node we are having this, we are keeping this information also. For this will help us for our problem, our dynamic order statistics problem. Okay, so let us take an example. So this is called order statistics tree, we can say. So this is the example of waste tree. This is basically red black tree. Okay, suppose these are the nodes. So CP A F N Q DH. Okay, so then we have the leaf nodes to make this. Okay, so this is our red black tree. And these are the nodes, these are the key. So, C is less than M. So, this M and A, B, C, D are in alphabetical order. So, the order they are coming in the alphabet, here they are, I mean A is less than C in the alphabetical order. So, that is why A is in the left side of the C. So, this is a red black tree, we can make the color of it also. So, now we need to put this extra bit of information, that is the, so this is the key value and this is the size. So, size of the tree rooted at this. So, now, so size is 1 for this node, size of this nils are basically 0, and size of, so this is 1 1, and this is also, this is basically size of the tree rooted at this. So, size is basically 3, size is 1, size is 1 1 3, like this. Now, what is the size of this? Size of this is basically size of the number of nodes rooted at this. So, 3 plus 1 4 and then 5. So, this is now, this is also this plus this 8 and plus 1 9. So, what is the formula we are using for size? So, size of a node is basically size of the left plus size of the right plus 1. So, size of x is basically size of left of x plus size of right of x plus 1. Okay. So, this is the, so size of left of x is 5, that means the left subtree, size of the left subtree is 5 for this node, size of the right subtree is 3 and the node itself. So, this is basically 5 plus 3 8 and plus 1. So, this is the formula for making the size. So, we can easily get the size. Now, suppose we maintain this size. Now, how it will help us to find the ith smallest element. So, that is called so we want to perform OS select. OS select. So, we want to get the ith smallest element in this. Okay. So, now, so for that we just, so suppose this is the red black tree and this is the x. Okay. So, now we want to find the ith smallest element, that is called OS select. Order statistics, but here dynamic on the dynamic set. So, ith smallest element. So, what we do? So, basically we start with this. If we write k is equal to size of left of x plus 1. Just if we do k is equal to size of left of x plus 1. Can you tell me what is the meaning of this k? So, basically, okay, before that let us take the root as a, so x is the, or maybe we can write there is more space. Yeah, so OS select t comma I. So, we just put x equal to root of t and then we take k is equal to the size of left of x plus 1. Okay, size of left of x plus 1. So, what is this k means? So, k is basically denoting the rank of x. Okay, why k is rank of x? Because see, I mean this is a red black tree. Now, red black tree is a binary search tree. So, if it is a binary search tree, then the in order traversal will give us the sorted array. I mean the sort, that is the BST sort. If you recall the BST sort, in the BST sort what we are doing? We are forming the tree, we are inserting the, we are forming the tree, and in the BST what we are doing? We are just performing the in-order tree walk. So, if we perform the in-order tree walk, that will give us a sorted array, and in the in-order tree walk basically it is the left subtree, then root, then the right subtree. So, that means the left size of the left. So, after the left subtree the root will be printed. Okay. So, that means the rank of that node, so will come after the printing of the all left subtree nodes. So, that is the size of the left subtree. So, that means position of x is basically in the sorted array is basically size of all nodes, I mean size of the left subtree plus 1. So, this means k is basically rank of x. Okay. Basically, this is coming from in-order tree walk. Okay. Now, we got k. Now, if so, suppose we are looking for I mean kth smallest element. So, if I is equal to k, then we are happy, we return x. Okay. Otherwise, if we are not so happy, I mean if we are not so lucky, I mean if we are just get the k which we are looking for, kth smallest element, that is the root itself. Otherwise, what we do? If I is less than k, else if I is less than k. So, that means we know this root is the say kth smallest element, and we are say this is the 7th smallest element, say yes, this is 5. So, this is the 6th smallest element. Suppose we are looking for third smallest element, then I is less than k. So, what we have to do? We have to look at the left part of the tree. Okay. So, then if I is less than k, then we just look at the, then we call OS select with left of x comma I. Otherwise, if I is greater than k, if I is greater than k, then we have to look at the right part of the tree. Then we have to call OX select again, right of x comma, but we have already seen the kth smallest. So, I minus kth smallest in the right part of the tree. Okay. So, that is the OX select. Now, let us take an example. Suppose we are, for this case, suppose we are looking for say fifth smallest element in this example. Okay. Suppose we are looking for fifth smallest element, we have a q over here. Okay. We are having q over here. So, this is the complete tree. I mean, okay. Now, suppose this is our set, this is our set S, and we have this structure, we have the this data structure, which is basically a red black tree, but we did some augmentation there by adding this extra field, that is the size, we are keeping the size of the tree. Now, suppose we are looking for fifth smallest element. So, we just execute this code OS select. So, we come here, this is x. So, what is the k value? K is basically 6, but we are looking for fifth smallest element. So, k which is not the case over here. So, that means we have to go further. Now, I is less than 6. So, we have to go for the left part of the tree, and this is our x now. Okay. And here also we are looking for fifth smallest element with this. Now, what is the rank of this? Rank of this is basically k is basically left subtree is 1 plus 1 2, rank of this is true. So, now I is greater than this. So, we have to go for the right part of the tree, and this is our x, but now we have already seen the second smallest. So, we are looking for fifth smallest. Now, our I is basically this I minus k. So, third smallest element in this subtree we are looking for. Now, what is the k over here? What is the rank of this node? Rank of this node is again 2. So, now I is greater than, so we have to go for right part of the tree with x is this, and but with I value is basically 1. So, this is our so what is the k? K is basically 1. So, we are getting, so h is basically fifth smallest element is basically h. So, h we return. So, this code will return basically h. Okay. So, this is the OS select. So, this set is dynamic, that means any we can insert a node over here. Suppose we can insert a node over here, we can delete a node over here. And so, what is the running time of this code? Running time is basically order of log n, because we are just going to the height of this tree. When you are searching, we are just going to the height of this tree. So, that height is, this is a balanced tree. So, that is why time for OS select is log n. Okay. So, that is the advantage of having the balanced data structure, balanced tree. So, this is a balanced tree, and so the height is h, and we are executing this, we are going at most the height comparison. So, that is why it is order of n. Okay. So, now the question is how we can perform this insertion and deletion operation, and now the yeah. So, how to perform insert and delete operation here. So, this is the dynamic order statistics. So, this is Q. So, suppose you want to insert a node, say, which is basically K. Suppose you want to insert a node K. Okay, we want to insert K. So, what we do? We just K is alphabetically less than M, we will go to the this side, K is greater than this, we will go to the this side, K is greater than this, we will come here, K is greater than this, we will insert K over here. Now, once we insert K, we need to change this field, like, so this is now became 1 and this will become 2 now, and this will become now 4 and this will become 6 and this will become 10. Now, all the path it will be changing. So, this operation, and not only that, then again we have to make this tree as a red black tree. So, for that we need to do those red black tree insert operation. So, in that case we need to maybe perform the rotation operation. So, we have to see in the rotation operation how we can handle the rotation operation, whether it is easy to handle. Basically, we need to handle this extra bit, extra information, that augmenting things. So, if we can handle this extra information in a constant time or in the same time with the red black tree rotation, then we are in then there is no issue. Okay, so, now we will talk about how to handle this rotation operation for a this for this extra information. So, suppose we have a tree like this E, then we have C, and we have a tree hanging over here with 4, 4, 7, 3. Now, we want to see up E down. So, this is basically right rotate on C. So, C will be up and E will be down, sorry, C will be up, E will be down, and the left part. So, this 7 will be hanging here and 3 will be hanging here, 4 will be hanging here. Okay. Now, how to make these changes? Now, this is basically this plus this 11 and this is basically 15 and this 16. Now, here also we can just change this. So, this is 3 plus this is 8 and this is also 16. So, this is also similar. I mean, to maintain this extra bit of information, we are not really using, we are just using constant time, because just we are because these are not changing, these are alpha, beta, gamma. So, these are not changing, we are just changing these bits. So, these bits is can be maintained in constant time. So, if this is maintained in constant time, then the insertion, so insertion or deletion can be done in logarithm time. So, this is most important. So, this dynamic set, we can preserve this set again, this red black tree by logarithm time, that is important. Okay. So, now the question is, instead of storing the subset size, so our augmentation is, we have the key value, here we are storing the subset size. Now, if we just store the rank itself, if we do this type of augmentation, then what is the issue? If we can store the rank, then we can just look at the this looks like easy to search the ith smallest element. Basically, we need to search the element whose rank is I. But problem with storing the rank is, now suppose we insert a node which is a minimum than the all other node which have. Then we need to change all the elements. The rank will change, because if we have inserted minimum or maximum element, then the rank of each node will change sorry. So, in that case it will take it will not take height time, it will take the order of n time. So, the keeping rank is not a good idea sorry. Okay, so, let us just write the methodology for this data structure augmentation. Okay, in the data structure augmentation, basically we have seen the we have to choose a order statistics, which is sorry, we have to choose a data structure, and in that data structure we have to do some augmentation. So, basically we have to choose a underlying data structure data structure. So, here we have taking the red black tree in our example. Okay. And then we have to decide, based on our problem we have to decide the augmentation things. That means, we have to determine the additional information, determine the additional information to be stored additional information to be stored. For our case, for our OS select, we store the subset size, subtree size. Okay. We did not store the rank of a node, because it will not help us. Then we have to verify the modifying operation. Verify how we can maintain this additional information, verify that this additional information can be maintained for modifying operation. Maintain in the same timing. Modifying operation means insert, delete, insert a node, delete a node. Okay. So, this is basically the methodology behind the our data structure augmentation. Basically, we take a underlying data structure, then we put some extra bit of information based on our problem. So, in the next class we will do another problem where we have to use the data structure augmentation, which is called interval trees. So, we will discuss in the next class. Thank you.